Before we get started here, guys, on wind patterns and distributing solar energy here, another thing to tell you about, okay, because I think I forgot to mention this to you guys yesterday. Over the next couple of weeks, okay, obviously you can come in and see me in scheduled help if you have any questions. My room is available at lunch hour, okay, every day, so you can come in and have a quiet place to work or study or ask questions, okay. After classes are over. All right, so after next Friday, if you have questions or you want to see me about something in relation to your final exam, please make sure that you come in or that you send me an email and let me know when you're coming. Okay, we're all here all through exam week. Okay, but we're usually trying to get things done for second semester, so some of us camp out in the photocopy room, for a couple of hours at a time, things like that. So if you just come in thinking I'll be in my classroom, there's about a 50-50 chance of that. Okay, I'm in the school, but I may not always be in my classroom. So if you have a question, just send me a quick email saying, Mr. Coder, I want to come in around this time, and I'll make sure I'm here. Okay, and not hiding in the photocopy room or wherever. All right. So there should be no times that I can't be here for you guys during exam week, okay, because yours is my first exam and I'm not supervising any exams until you guys write. Okay, so if you just send me an email, say, Mr. Coder, I'd like to come in around 10 o'clock on Monday, that's fine. Okay, I'll be in here. Everybody got that one? All right. I don't think there's any issues in this particular class, but if you are missing any assignments, okay, they must be in by next Friday. All right. I will not accept anything after the last day of class for marking. All right. So if you are missing any assignments, you got any NHIs, check your Power School. If you are missing anything, I must have it by next Friday. After that, I will not be marking anything. Okay. Reason being, sometimes people take the chance in that, well, I got 48 right now. I got 5 things I didn't hand in, but I'll just get 52 on the final. Well, actually, you'd have to get more than that. But anyway, I'll get whatever 60% on the final, and I'll pass the course, and I won't have to hand those things in. Then they don't do well on the final, they don't pass, and then they're coming in and going, Mr. Coder, oh, can I hand in those 5 things I didn't hand in? No. Okay, should have handed them in before. All right, so the absolute deadline for things to be handed in for our assessment is the last day of class. Okay, please make sure I have them by then. Okay, I don't think that applies to anybody in here, but in case it does. All right, and remember, final exam, January 22nd, 9 a.m., okay, in the gym. Now, when you are writing in the gym, a couple things to be aware of. The doors to the gym open at 8:45. All right, so you'll want to be here around the time you would normally get here for class on a regular school day. Okay, that way you can just kind of hang out for a little while, have everything sort of ready to go. When the doors open, there's always going to be a big whiteboard, portable whiteboard on wheels, okay, in the hallway, and it'll tell you what row you are in. All right, so it'll say, row 1 is Science 10 AP with Coder, and it'll have the first person's last name. So in this class, that doesn't matter. Anyway, the first person starts with the first person in the class, okay, and then the last person in that row, their last name. If you're in between those 2 last names, you go to that row and you walk down the row until you find the test with your name on it. All of the tests will have names on them. All right, you have to make sure you sit down at yours. I mean, you can write somebody else's, but they'll get your mark. Okay, so yeah, if you're going to do all that work, you probably want it to go towards you. Okay, everybody got me there? Okay, things you can have at the final exam. Okay, things you should bring. Might want to write this down. Pencils, bring a couple of them. All right, like a couple means at least 2 pre-sharpened. Okay, bring them pre-sharpened. They don't come that way when you buy them, but you'll want them that way. Okay, make sure you sharpen them, okay, before you come in, or have mechanical pencils that are full of lead, whatever. Have 2 pencils. Have 2 pens. All right, always best to have a backup. Because I've seen people, they come in, they only have 1 pencil. It looks like it came from a golf course. It's about this long. Okay, it's worn down to the nub. There's no eraser on it, and they're trying to write their test, and it breaks. Okay. There are going to be at the most 4 supervisors in the gym. There are several hundred students in there at one time. It may take us a while to get to you if your pencil breaks. Right? It would be nice if you didn't have to just sit there doing nothing for 5 or 10 minutes, okay, while we get you a new pencil. All right, so always have a backup. 2 pencils, 2 pens. Right? Not a bad idea to have a straight edge. Okay, even just a small one. Okay, you may or may not need it, but okay, not a bad idea to have one. Your calculator. In your calculator should be fresh batteries. Okay, for this reason. You don't want them to crap out on you in the middle of the test. All right, I've seen it happen, and it is very stressful for that person. All right, because it takes me a while to go get you a new pair of batteries. Okay, I have to go all the way to Miss Wrestler's office, get new batteries, come all the way back. Okay, it's a pain in the neck. The other reason is sometimes when I'm clearing your calculator, I'll get the batteries low, please replace. That means I can't clear your calculator. I have to go to Miss Wrestler's office and get a new set of batteries to clear your calculator. So I put them in, I clear your calculator, then I take them out and I put your crappy batteries back in. Okay, I'm not giving you a free set of batteries. Okay, and that takes a while. And I don't just go and do that for you and then come back for everybody else. I do everybody else first, which means you don't have a calculator until I'm done clearing everybody else's calculator. Does that cost you time? Is that stressful? That would be stressful, okay? You want to avoid anything that's going to stress you out, okay, during a final exam. So please make sure you put a fresh set of batteries in your calculator and test them, okay? Because I've had people who bought a bad set, okay? They put 4 what they thought were brand new batteries in their calculator, and it didn't work. All right, but they didn't test it until they got into the exam and went, oh, crap, okay? You don't want that situation, okay? So make sure you put new batteries in and check that they work. All right? Everybody with me there? All right, so we got 2 pencils, 2 pens, and a calculator, and a straight edge. That's it. That's all you need to have, okay, for your final exam. You will get a fresh formula sheet and a fresh periodic table. Okay, you can't bring yours in because I have no idea how much stuff you've written on it. You've probably lost your periodic table by this time. Okay, so you'll get fresh ones for the final exam. You don't need to worry about those. Okay, I would also suggest you bring some water, maybe an exam-appropriate snack. Okay, an exam-appropriate snack would be something you could eat quietly without disturbing other people, like fruit or a granola bar, okay, something like that. A 500-gram bag of Doritos is not really an exam-appropriate snack. I did have a person do that one time, and I thought the people around them were going to kill them. Okay, they're ruffling the thing, trying to get the bag open, and they're chewing with their mouth open, crunching Doritos. Okay, it wasn't very appropriate, wasn't very polite or thoughtful. Okay, so I would suggest make sure you have that. Okay, and that's about it. Things you cannot have at the final exam. You may not have any electronic device that is Wi-Fi or 3G enabled. Okay, which means you can have your calculator, nothing else. Okay, you cannot have a tablet, you cannot have your phone, you cannot have an iPod, any of those things. Anything that can connect to the internet or in any way cannot be in the exam room with you. So, leave them in your locker. Okay? Don't bring them to the exam because we collect them and we put them in a box, okay? And then we put them in like Mrs. Ostafachuk's office and lock them up, which means you don't have it, and then if Mrs. Ostafachuk's not there when you're done your test, you have to wait for her, and it's just inconvenient. Leave all that stuff in your locker, okay? Leave your coat in your locker, okay? Don't bring it to the test because we make you leave it in the hallway leading into the gym. And unfortunately, there are dishonest people who, on their way out of the exam, like to rifle through people's coats looking for things. Okay, so don't bring your purse, wallet, carry-all, okay, that kind of stuff to the exam. Leave it all in your locker. You don't need it. Okay, everybody clear on that stuff? Okay, so just little things to think about. Okay, we'll talk a little bit about final exam strategy next week. Okay, but those are some of the things that you'll want to look into getting for the final exam. Okay, distributing solar energy. Okay, we have to look at how energy is distributed on Earth. We talked a bit about that yesterday. We talked about how it's transferred. What were the 3 things that could happen to energy when it struck the Earth? It can be absorbed, used by what process? Photosynthesis, and reflected. Okay, if it is absorbed, then the Earth can transfer it around. Okay? What are the 3 ways that heat can be transferred? Let's start with the most common, most important one. Okay, in the atmosphere, what process do we use? It starts with C. convection. Okay, convection is those moving currents of air that are the result of differences in temperature. Okay, there's also conduction. That's the transfer through solids. Okay, where the particles run into each other, and then there's radiation. Okay, and that is the rays that come in. Okay, radiating energy away in the form of rays or waves. All right, those are the three methods of heat transfer. Those things that we've just talked about are going to be important today because they are the things that cause wind. Okay, and wind is the way that energy is distributed on Earth. Okay, so we got to look at the role winds play in distributing energy. We're going to talk about the Coriolis effect, okay, and how it distributes energy, and look at global wind patterns, okay, as a product of both convection, okay, hot air rising, cool air descending, and the Earth's rotation. Okay, the Earth's rotation actually causes winds to have a certain direction in most places. All right, it's the cause of the prevailing winds. All right, questions there so far? Okay. So the Earth's atmosphere is in perpetual motion. That means it is always moving. Okay, perpetual means always, so it's always moving. The reason for that, nature doesn't like imbalance. So it's always trying to balance out differences in both temperature and what else could be different within the atmosphere from place to place? Pressure. Okay, differences in temperature and pressure are always trying to be equalized. The only way to equalize them is to move air. Moving air is wind. Okay, moving air is wind. That's convection. Okay, all right. So there's constant differences in pressure and temperature, and so we get this kind of stuff. Now, on this diagram here, you see this arrow, okay, indicating the direction the Earth rotates. Okay, so the Earth rotates in that direction. Okay, that is why if we are here in the dark, the sun appears to rise in the east. Okay, because if we were standing here looking to our left, that would be east. Agreed? Okay, and if we were looking to our right, we would be looking west. That's where the sun would set. Because when we're over here and the sun is setting, the sun is over there in the west. Everybody got it? All right, so the Earth spins that way. Now, if you are driving along in a car, and not that I recommend you do this, but you stick your head out the window, okay, does it feel windy? Does it necessarily mean it's windy outside? No, it feels windy because you're moving through the Earth's atmosphere. Everybody all right with that? Well, the same thing happens when you stand on the surface of the Earth. Okay, as you stand on the surface of the Earth, you, to some extent, move through the air. The air is not physically attached to the Earth. All right. It spins as the Earth spins, but not always at exactly the same rate. Okay, and so to some extent we're moving through the Earth's atmosphere as it rotates. It's not like when you stick your head out the window of a car, but it's similar. Okay, all right. So to us, if we were standing here and the Earth's atmosphere was perfectly stationary, it would feel like the winds were going this way because we would be moving through them. You guys follow me on that? Right? Whenever you stick your head out the window of a car, it always feels like the wind is going that way, right? Behind you, towards you, or okay, but it's not really. The air could be stationary. You're just moving through it. All right. So, distributing Earth's energy. Okay, nature doesn't like imbalance, so variations in temperature create variations in pressure because hotter air tends to be less dense. Okay, and so exerts less pressure, okay, than cooler air, okay, and as a result, air moves from areas of high pressure to restore the balance, okay, always from high to low, okay, whether it's pressure or temperature, nature always moves from high to low. All right. Okay, so wind in turn transports heat, energy, and moisture. Okay, we talked about that moisture stuff. Okay, moisture can carry what kind of energy? 2 words. Latent heat, right. Okay, so wind helps to carry latent heat in the form of water vapor, okay, from place to place within the Earth, okay, or above the Earth. All right. Okay, the jet stream is a big part of that. The jet stream is this very high altitude wind, okay, and there are several of them on the Earth, okay, that help to move large amounts of air around. Okay, they're the reason why the weather changes. Okay, they're the things that bring in these large air masses that can cause changes in weather. All right, so if you look here, this would be kind of your typical weather map here on the left. Okay, and this is your jet stream, the purple arrow. Now this is kind of showing how it moves, and its shape changes all the time. The shape of the jet stream is always a little bit different, okay, because it tends to move around high and low pressure areas. They kind of force it around itself. All right, everybody follow me there? Okay, so we got this high pressure area here making this area warm and dry, okay, and the jet stream is trying to go around it, okay, but over here, okay, we've got this chilly air being forced southward because there's another high pressure area here. The only place for the cold air to move is in between them, and the jet stream helps to push it that way. Everyone follow? Okay, so the jet stream pushes it through, okay, and you can see it kind of move along this direction. So if you were, let's say, in Regina or Saskatoon, okay, those kind of areas there, you would have it very cold. Okay, whereas if you were over here, okay, in let's say Grand Prairie, it would be warm. Right? This is how meteorologists predict the weather. They have to predict how these air masses are going to push the jet stream, because the jet stream is what will bring new weather to a place. So they have to predict and look at how fast is the jet stream moving, how fast are the high and low pressure areas moving, when will they arrive in certain places. Okay? Are they reasonably good at doing that? Most of the time, they're reasonably good at it. Other times, you just want to have your weather rock outside, okay? Because at least the weather rock is never wrong. Okay, you guys know what I mean? Right? The weather rock is the rock on a string. Okay? If the rock is moving, it's windy. If the rock is wet, it's raining. If the rock is dry, it's sunny. See, the weather rock is never wrong. Okay? It can't predict the weather, but at least it's not like sometimes when you open up the app on your phone, the Weather Network, it's snowing to beat the band outside, and the Weather Network says it's sunny and 5 degrees. Right? Okay? So sometimes that happens, right? And then you're like, where's my weather rock now? Okay? All right. So you got the jet stream pushing along through here, okay? And anywhere where the jet stream is moving, okay, you can see that there would be areas that would be unsettled. Unsettled because they're at the point of interaction between two very different air masses. So in this area here, it would be quite unsettled because it's warm and dry, but we've got this chilly, wet air moving down towards that. So in those areas where they interact, you get unsettled weather. All right? And that, of course, just happens to be kind of in the tornado alley type of area. Okay? Everybody follow there? All right? So the jet stream can help to move a lot of air very quickly. All right? And so it helps to distribute stuff between polar and tropical regions. Okay? Because typically, the Earth just on its own, without the jet stream, is always trying to move hot to cold, right? It's always trying to move that way, right? The jet stream helps to equalize and move stuff the other way. So they actually work opposite to each other. But it's okay because most of the weather stuff occurs near the Earth's surface, where the jet stream is quite a bit above. Okay, so they can actually go underneath or above each other. All right, now that is what can create unsettled weather. When you have one air mass driving itself underneath another one, where they interact, can produce a lot of unsettled weather. All right. Sometimes we'll have like a warm air mass, it's moving, and a cold air mass will try and cut underneath it. Okay, and when that happens, it starts to cool down the moisture in the bottom of that warm air mass that's trying to move above, and that's when we can get heavy snowfalls and things like that, because those two things are very different. Okay, and so they create sort of violent interactions. Yeah? All right, so that's the purpose of the jet stream. Okay, jet stream's important. Often, a question on a test might say, explain the role or explain how the Earth might distribute solar energy, and you would want to mention jet stream in there, okay, because it can help to move air masses that equalize temperature. Okay, prevailing winds. What way do the winds typically blow here? Okay, they blow to the east, so we call those actually, they come from the west, okay? So they blow from the southwest, okay? We call them westerly winds because they're always named from the direction from which they come, okay? So we have typically westerly winds from the southwest in our area, all right? And we are kind of right here, okay? Right in this area here. So we're right at the top of the prevailing westerly area, okay? And that's, of course, why we have the saying in Alberta, if you don't like the weather, wait 5 minutes, okay? Because we tend to be right at the point where you could have an easterly influence from the pole, or you could have a westerly influence from a lower latitude. Most of the time we get this westerly influence, but occasionally when the wind blows from the northeast, we're in trouble. Okay, that's when we get the nasty stuff. All right, so here's what goes on. You can see here convection currents. Okay, where does the most energy from the sun hit the Earth? At the equator. Okay, that's where the sun is most directly overhead, where sunlight is most concentrated, hottest part of the Earth. So at the equator, you always have hot air rising. Okay, and you can see that here. Okay, the hot air is moving. Okay, is moving up. Everybody with me on that one? Okay, as it rises, air from above moves in to replace it. Now, this air is still reasonably warm because it's still relatively low latitude. Okay, it's still relatively close to the equator. Okay, this hot air that's risen begins to cool, but it can't fall back down where it came from because this air right here has moved in to replace it. So it's forced northwards. Okay, as it's forced northwards and begins to descend, it can encounter air from that area. Okay, but air from that area tends to be a bit cold by comparison. Okay, certainly this equatorial air that's risen and gone to a high altitude has cooled somewhat, but it's still warm compared to the air that was in that more northerly latitude to begin with. Okay, so what you get is air that is cool. Okay, this stuff kind of cool from the equator trying to move northwards, along with some cooler air trying to move northwards. You get this weird convection thing happening, and because they're trying to move northwards, okay, we get typically south prevailing winds. Okay, the winds tend to come from the south because they're moving towards the north. Everybody with me so far? So what makes them go east? If they're trying to move from south to north, what makes them go east? Don? The rotation of the Earth. Okay, it's not that they're moving east; it's that the Earth is rotating underneath them as they try to move north. Okay, and so then it's like you stick your head out the window of the car. All right, they're trying to move north, but the Earth is rotating. Okay, and as it rotates, they get deflected. All right, and we kind of move through them, creating this kind of westerly effect. Okay, everybody follow me there? Okay, at the equator, it's different. Because they're trying to move down, they actually get deflected this way. Because remember, the Earth is rotating this direction. Okay, so as winds try and move south, they get deflected west. As winds try to move north, they get deflected east. Okay, up here at the pole, winds are trying to move south again, so they get deflected west. Okay, everybody okay with that? All right. So this is what kind of influences our weather around here. Most of the time we're in the influence of these southerly winds, okay, that are blowing towards the north but coming from the south, okay? And as we rotate this way, okay, the winds kind of get pulled along. Here, they try and move the opposite way, okay? And at the pole, they're trying to move south, so they get deflected, okay, to the east. That's called the Coriolis effect. Okay? The Coriolis effect is this deflection of winds because the object spins, or the Earth spins, underneath the atmosphere. Now, I usually have, sitting around somewhere, as the Earth turns, it deflects the moving air, or it makes it appear as though the moving air is being turned in a particular direction, and that's what causes our prevailing winds. Okay? Typically on Earth, the winds are only trying to move north or south. All right? But because the Earth spins underneath, it appears as though they come from east or west. Everyone's good with that? Okay? The jet stream, obviously the jet stream can wreak some havoc on that. Okay? But remember that the jet stream is temporary. It moves around a lot. It gets pushed in all different kinds of places, and that's why once in a while we get just this, like, wind out of a really weird direction. Okay? When that's happening, you know something big is on the way, because the natural tendency of the Earth has been overcome by a temporary move of the jet stream. Okay? Now, for us, that means weather. Okay? If you are, let's say, at a very high altitude, a moving jet stream can be very dangerous. Okay? People that are climbing very high mountains have to be very mindful. They have to watch, okay, the jet stream, because if it moves in, they could be in an area where its wind speed plays a factor for them. All right? The jet stream can move between 110 to 300 kilometers per hour. If you're on top of, let's say, Mount Everest when that happens, okay, you could be facing winds in excess of 150 kilometers per hour. Okay, not a good thing if you are standing on the edge of a precipice. Okay, and it's a complete whiteout because the wind's blowing 150 kilometers an hour. All right, so they have to be mindful of that. And how can they tell it's coming? Well, they have satellite weather imagery, same as we do. Okay, but sometimes it's just common sense stuff. They watch the tops of the other mountains nearby, and if they can see snow blowing off the tops of the other mountains approaching them, it's time to go home. Right? If you stay up there and you see that the wind is affecting peaks nearby and moving towards you, okay, and you stay there, you're going to get caught in it. Okay, so they often will look for that. It's called spin drift. Okay, because it looks like it just spins the drifts off the tops of the other mountains. So it's something to watch for if you're at high altitude. Okay, so does everyone sort of follow this? Okay, so we got the convection and the spinning of the Earth working together. All right. Okay, so this is just further explanation of that. Okay, you've got these convection currents. Okay, wind trying to move north or south. Okay, wind, Earth spinning underneath causes that change in direction. Okay, here in the horse latitudes is what they call it, where the westerlies happen. Okay, you've got that opposite deflection, and then the polar easterlies move just like down here. Now, some technical names, or common names, I should say, for some of these winds. Okay, down here at the equator, these are called trade winds. Okay, the easterlies that occur near the equator are called the trade winds. Okay, because way back when, they were used to bring traders over from Europe to the New World. Okay, because they blew in the right direction. Okay, if you wanted to sail back to Europe, you couldn't do it near the equator. Why not? The wind doesn't blow the right way. So what you would have to do is sail up the coast, okay, to a high enough latitude that you could catch the westerlies and then start moving back towards Europe again. Okay, and so it was kind of an important thing for people to realize. All right, so and then up here, obviously they're just called prevailing westerlies up in our area, okay, and then these are the polar easterlies up top. Okay, once in a while, just so if on a multiple choice question or something, it uses the term trade wind or polar easterly, you know what they're talking about. Okay, so this happens anywhere you have an atmosphere. Okay, you'll have this convection because light comes in more at the equator than it does at the poles, so you always get this kind of effect here. The bigger the planet is, the more bands of these convection currents you will see. Okay, on Earth is only big enough to see 3 bands. One at the equator, okay, one above the horse latitudes at 30 degrees, and one above 60 degrees. If the planet is much bigger than Earth, you may get several lines of those per hemisphere. All right, so more than 3. Best example, okay, Jupiter. Jupiter almost looks striped. Okay, most of the gas giants, if you look really closely, have stripes. Okay, going from the equator up to the poles. Okay, and you can see here that on Jupiter there's way more. All right, and I'll show you a video here in just a second where you can actually see the stripes move in different directions. They move right opposite each other. Okay, it looks pretty funky actually. And around the Great Red Spot, that's one of the best places to see it because the red spot rotates. Okay, and the winds on either side of it go in opposite directions. So you've got winds going one way on one side. I think it's this way, and this way on the bottom. It might be the opposite, but okay, they move in opposite directions. Okay, and that's caused by exactly the same thing. This is all gas, okay, and the sun's energy hits the equator more than it does the poles. You get convection currents happening, and Jupiter spins very fast. Okay, a day on Jupiter is 12 hours. Well, between 10 and 12 hours, something like that. Okay, so does it spin pretty fast? Yeah, quite a bit faster than Earth, because not only is its day less than half as long, it has to spin a lot further to go all the way around, because it's so much bigger than we are. Okay, so it spins very fast. All right. Okay, so now you can see that, okay, that kind of happens, and I had those drawn the wrong way. It actually goes the other way. Okay. You can see there that that convection still works, okay, and obviously the lighter the gases and the faster the rotation, the faster the winds are going to be. Hydrogen's quite a bit lighter, okay, than the gases our atmosphere is made out of. Okay, Coriolis effect. So that's what I demonstrated there with the basketball a few minutes ago. Okay, so the Coriolis effect, okay, causes this deflection. Okay, this was our intended path here. Okay, we wanted to draw a line that was straight down, okay, from the pole to the equator, but because the Earth rotated underneath it, okay, it was deflected and ended up over here. Right? That's the same thing that happens to winds that are moving from north to south. Okay, so the deflection of any object from a straight path is caused by that. So Coriolis effect, okay, an important thing to know. That is the main cause of the prevailing winds. Okay, why winds come from the east or come from the west prevailingly on Earth is because of the Coriolis effect. Okay, questions on that part there? All right, give you a few minutes. I want you to answer those questions. Then we'll go through them, and then we're going to move on to heat capacity after that. All right, so very simply, what's the effect of unequal distribution of thermal energy on Earth? In one word, wind. Okay, that is the effect. Movement of air, convection currents, wind. Okay, because it's not equal and nature doesn't like imbalance, nature moves the air to try and make balance. That's wind. All right. Explain how the Coriolis effect influences the direction of winds in the northern hemisphere. Okay, well, any winds that are trying to move from north to south get deflected west. Okay, any winds trying to move from south to north get deflected east. Okay, that's the summary of it. That's what happens. Okay. All right, what are the trade winds and where do they occur? Right, okay, they're at the equator. They are generally easterly. Okay, actually they would be northeasterly because they would blow from the northeast. Right, yeah, okay. And what are jet streams? Jet streams are those high altitude winds that move as a result of locations of high and low pressure, okay, helping to equalize temperature differences. Okay, any questions on that stuff there? Everyone's good with that? Okay. All right, next thing we got to talk about is heat capacity. Okay, this doesn't have to necessarily do with winds or weather or anything like that. Heat capacity has to do with how quickly something can change its temperature. All right, you probably noticed that some things change their temperature very quickly, and other things take a very long time to change their temperature. Okay, for example, if you put an empty pan on the stove and turn the stove element on, it's not long before you can't touch the pan, is it? Okay, but if you put water in that pan, does it take a lot longer for the water to be so hot you can't put your finger in it? Yeah, okay. Water has a very high heat capacity. That means it takes a lot of energy for water to change its temperature. Okay, whereas most metals are the exact opposite. Most metals have a very low heat capacity, which means very little energy is required to make them change temperature. All right. Think of it like this. If somebody, let's say, takes like a spoon and it's been out in the cold, and they put it against your skin, is it very long before it doesn't feel cold anymore? Right? Like they put it on your skin, and initially it's like, whoa, that's cold, but it's like a couple of seconds, and it's already the same temperature as your body, and you don't notice it anymore. Okay? But if somebody has been outside and their hand is very cold, and they stick it on you, does it take a while before that hand doesn't feel cold? Yeah. Okay? Because what are they made of mostly? Water. Okay? Water has a much higher heat capacity than metals do. Okay, and so it takes a lot longer to change the temperature of something with a high heat capacity versus something with a low heat capacity. All right, so that's what heat capacity is. Now, there's two different types here. There's heat capacity and there's specific heat capacity. Heat capacity refers to an object that may be a mixture of several different materials. All right, so a heat capacity is kind of the average of all of them as they in their various concentrations within an object. Okay, specific heat capacity has to do with this material and when it's all by itself. All right, everybody with me there? So the human body has a different heat capacity than water does because the human body isn't just water, right? It's lots of other things, all right? So on average, the human body has a lower heat capacity than just plain water does, okay? All right, so definition-wise, okay, the real difference here is heat capacity deals with an object, okay, whereas specific heat capacity deals with a substance. All right, everybody follow me there? Here's the other things we need to keep in mind. Mass and temperature. All right, for specific heat capacity, all right, it's given as a number, okay, but it's in joules per gram degree Celsius. Okay, that means when I tell you that the specific heat capacity of aluminum is 0.9 joules per gram degree Celsius, that means it takes 0.9 joules to heat 1 gram of aluminum by 1 degree Celsius. Okay, everybody follow me there? Okay, whereas for water, it takes 4.2 joules of energy to heat 1 gram of water by 1 degree Celsius. Is that a considerable difference? Yeah, it's almost 4.5 times, right? Like it's big. Right? Water takes a lot more energy, okay, than aluminum does. Okay? And things like copper and silver are even lower. All right? Okay. So, like we said, units for specific heat capacity are joules per gram degree Celsius. All right, so most often we're going to be dealing with this. All right, it's very difficult to do problem solving using heat capacity because it's related to an entire object. So we would need to know the mass of the object and all of that kind of stuff. And so we don't do it very often. Most of our problem solving will be related to specific heat capacity and this formula right here. Okay, E equals m times c times delta T. What does delta mean? Change. What does the T probably mean? Temperature. Okay? So, okay, E is energy, M is mass, C is specific heat capacity, this thing we just finished talking about, and delta T is the change in temperature. All right? Everybody with me so far? All right. Now, let's say I want to solve for energy. Do I have to do anything to this formula? No. Okay. Let's say I want to solve for C. What do I have to do to that formula? Right, divide by m times the change in temperature. So C will equal E divided by m delta T. Now, let's look at units. What are the units for specific heat capacity supposed to be? Joules per gram degree Celsius. All right. E is in joules, right? Energy is always in joules. Mass is in grams in this unit. Okay? And delta T is in? Does that give me the units I'm looking for? Yeah. Okay? All right, is that a pretty easy formula to manipulate? Yeah. The only time that you might get a little bit of a trick would be if the question told you, asked you to find, let's say, the final temperature of something. Okay? The only difference that makes is delta T actually means m times C times TF minus TI. Right? It doesn't really change a whole lot. Okay? You would just do this. Okay, and solve for one of the two. Is that all that difficult? Okay, I think you guys can probably figure that one out. All right, so what we're going to do is a little bit of kind of problem solving to do with this formula. I'll go over a few examples, and then we'll do a little bit of practice with that, and then probably by halfway through period tomorrow, we'll be moving on to latent heat. Okay, we'll work on that on Thursday and maybe a little bit on Friday. Over biomes on Monday, review Tuesday, and we're good to go. Okay, we'll be finished on time. All right, so rather than go straight to those, let's go over a couple of examples here. So, Okay, so that would be kind of a typical heat capacity question. All right, how much energy or heat is needed to raise the temperature of 150 grams of water, whose specific heat capacity is 4.2 joules per gram degree Celsius, from 5 to 85 degrees Celsius? All right, so should we write down our givens? Same as we do with any problem-solving thing, right? So M equals 150 grams, C equals 4.2 joules per gram degree Celsius. I don't know why I have degree up there. Okay, joules per gram degree Celsius. And the change in temperature, 85 minus 5 equals 80 degrees. Okay, looking for E. All right, is that a very difficult calculation? No. Okay, formula is E equals MC delta T. Okay, 150 times 4.2 times 80. Okay, gives us 50,400 joules. Okay, does that make sense? Everyone's good with that one? Okay. Can I move on to another one? Is everyone done copying that one? Oh. Okay, another way a question could work, it could be I would actually have to do this one prior to doing this here. Okay, so you could have a question that works like this. Now, you are going to be given a chart of specific heat capacities here shortly. Okay, but if I was looking for what material this thing was made out of, what part of the formula am I most likely solving for? C, right? Because specific heat capacity is a physical property, right? We talked about that back in chemistry. It is unique to each material. Right? And so if I solve for C and then had a chart, I could look up the number I calculated and see what material it corresponds to. Right? So in a question like this, okay, we would again write down our givens. E equals 4,200 joules. Okay, the mass of the container or cup here is 100 grams. Okay, and the change in temperature is 50 degrees Celsius, 62 minus 12. Right? We're looking for the specific heat. So E equals MC delta T. All right, and we're manipulating for C, so we divide both sides by M delta T. All right, and we're left with 4,200 over 100 times 50. Okay, and that, guys, has to be done in brackets. We need to divide the top by the bottom, not the top by 100 and then multiply by 50. Doesn't give you the same answer. Okay, and that should come out to 0.840 joules per gram degree Celsius, I believe. Okay, which corresponds to glass. All right, everybody good with that? Be able to handle using this formula? Okay. Because I just told you, you'll have a chart that has all of the numbers on it, right? So when you solve this and you get 0.840, you look on the chart, find 0.840 and what it corresponds to on the chart. Okay? All right, so I'll hand out a worksheet here. You guys can work on it for the next 15 minutes or so. Okay, you'll probably get pretty much done, okay, because it's pretty straightforward.